All right, everybody, let's get started. Welcome to the ScaleSim tutorial at ASPLOS 2021. I can see some of you are online, some of you are trickling in, so we can basically get started. So I'm Tushar Krishna. I am an associate professor here at Georgia Tech. And today I'll be co-running this tutorial along with my student Anand Samajdar, Jan Moritz Joseph, Paul Watmo, and Yu Hao Zhu. This is a broad overview of the schedule. So I'm gonna, I've kind of kickstarted things by just welcoming you. I'll give a brief overview about what this tutorial is about. Then we're going to have Paul and myself give you a brief introduction to just deep learning, DNNs, and accelerator design, just to kind of set context to what the tutorial is going to talk about. Then we'll have a deeper dive into ScaleSim that Anand, Moritz, and Paul will go into. And after that, we have 3 tutorials that are kind of getting your hands dirty with using ScaleSim. So the first one will be a design space exploration piece using ScaleSim. The second tutorial will go into modifying ScaleSim to add custom features. And the last tutorial will look at using ScaleSim to build larger simulators. And at the end, Yu Hao will kind of lead a discussion on the future roadmap for ScaleSim, some of the planned features, and try to get ideas from the community. This is the ScaleSim tutorial website right here. At the end of each of these, we'll have a brief Q&A. The slides and videos will be available on this website. Once the tutorial is done, the recordings will appear there as well. I do want to kind of mention that the tutorial is being recorded. And so in case, that is, I just wanted to explicitly know that in case you want to turn off your video, in case you want to take care of that, please do that. Your Q&A will also, of course, get recorded as part of that. And finally, please do interrupt us and ask questions over Zoom. Or you can use the Clouder chat. So we will be monitoring the chat window on Clouder and you can ask questions there. So with that, this is a brief overview of what we're going to talk about at the very beginning. So let me talk a little bit about what this tutorial is going to be about, and then share some, links to resources that will be useful. And then, we'll do a deeper dive into some of the relevant background to understand the rest of the tutorial. So what is this tutorial about, right? So, I mean, of course, we're all in this deep learning era where DNN models have shown massive improvements in accuracy across tasks, right? In vision, recommendations, speech, and so on. And within the deep learning landscape, you typically start by creating a model, you train it. This is an iteration that goes on. Once you have a trained model, you deploy it for inference. And inference, of course, could be on the data center or on the edge. And within this context, there's a bunch of design tools we use throughout this process, right? So for model creation, TensorFlow, Caffe, PyTorch are very popular. For training, there's a lot of libraries that are available to help you train your model and get efficiency. Once you deploy it, there are libraries available like TensorRT. There's a few other recent ones that help you, optimize the model and deploy it for inference. But there is a lack of tools on the extreme end, which is on actually designing accelerators for inference. And this is where ScaleSim comes in. So the focus of this tutorial will basically be on this end, right? How do you leverage an infrastructure like ScaleSim to help you design acceleration platforms? So some of the resources that you should be that you can kind of get access to is the first is the ScaleSim webpage, the GitHub page, and the tutorial page. So once you get to the ScaleSim webpage, there are links to all of these other things. This is the GitHub page for ScaleSim v2 that we're releasing today. You also have, of course, the link to the ARM page where the first version of ScaleSim is currently hosted. And we'll talk about this in the tutorial today. And these are some other resources I do want to point you all to, like, between some of the presenters here, we've participated in writing some of these synthesis lectures related to deep learning accelerator design. And I encourage you to check these out as well. They will do, of course, a much deeper dive into the process of accelerator design. So with that, welcome to the tutorial. And as I said, this is the agenda. So what I'm going to do right now is hand it off to Paul, who's going to introduce DNNs for you. So let me stop sharing. And Paul, you can go ahead and start sharing.
Okay. Can you see my screen there?
Yes, it's visible.
Excellent. Thank you, Tushar. Thanks for the introduction. Welcome everybody to the tutorial today. Excited for this one. So apologies if there's a little road noise behind me. It's actually snowing today in Boston, so there's some commotion outside. I think this might be the sort of least useful part of the whole tutorial today, but the goal here, I have a few slides, and the goal is to kind of perhaps frame where we're at with deep learning hardware, and at least from my perspective, what the pull is for simulators in this space and research generally in this space. So my name is Paul Watmo. I'm with ARM ML Research here in Boston. So let me start with this slide. Some of this echoes Tushar's comments previously, but I guess in case it's not very clear to people here, deep learning is definitely driving really strong growth in edge computing and beyond. I mainly focus on edge computing personally, but obviously also applies in the data center and in essentially everywhere computing is happening, I think it's fair to say. So, I mean, in terms of edge computing and mobile devices, we've seen a huge explosion in recent years. A lot of this is resulting in computing perhaps in areas you traditionally don't expect to see it. So, for instance, we're seeing a lot more computer vision driving computing in cars. We're seeing it in autonomous vehicles. We're seeing it in things like surveillance cameras, which traditionally would just generate some kind of information feed, but increasingly we're doing computer vision there as well to actually try and reduce the amount of data we communicate and filter it essentially to extract the information. So there's a huge range of stuff here. I think in terms of real products, the two areas I would say where deep learning is having huge impact is computer vision and natural language processing. Essentially, processing camera, video data, and processing audio data of some kind. There's other stuff as well, for sure, but I think these are two that are really driving edge computing right now. So I mean, I'm kind of mainly going to touch on inference here as well. Obviously, training is absolutely necessary, and we're seeing more training happening on edge devices as well. That's kind of a whole other thing, perhaps for next time. But I think most relevant for Scaleson today is inference on the edge platforms. So I think if you consider these types of devices, I think it's quite amazing what we're doing with them. So these are all battery powered devices, yet even the car here, the automotive applications, battery powered, right? So we really care about energy efficiency. It's really important. We also care typically about throughput. There's nearly always some kind of real-time throughput constraint driving these applications. So for things on mobile, like augmented reality, we have to keep a fairly high frame rate, maybe 15, 20 frames a second at least, so that when you move your phone around, you'll get a smooth user experience. Similarly, for things like ADAS and L4 self-driving cars, things like this, latency is obviously absolutely critical because we need to detect objects in the roadway and things like this that we then perhaps have to maybe apply the brakes or something like that to avoid. So some kind of real-time throughput constraint. So throughput constraints and energy constraints, this is what drives hardware design. I guess one thing on the bottom right here I've just mentioned is TinyML. So I mentioned here, I guess this sort of hints at hearing aid applications. I think this is another area where deep learning is having a really big impact, and I think there's potentially a really long tail of applications where very low power deep learning can really enhance existing products and sort of generate new ones. So I think this is kind of what I see in terms of the landscape of devices and applications that are impacted by deep learning. Okay, and then just to touch on the machine learning side briefly, in terms of where we're at with that. So I think the general trend kind of that kicked off deep learning, I think, kind of still holds to a large extent. So the trend is that being able to train larger models tends to give high utility, meaning higher accuracy on some task we care about. The last year or so, natural language processing is definitely the poster child for this. So we've seen transformers and variants of that are able to train with huge number of weights, hundreds of billions, if not, just starting to push the trillion parameter point. And these models, have incredible capabilities in terms of essentially being able to process text and generate text in really, human-like convincing ways and capture a lot of information. So that's a really interesting trend. I think it still holds. Let's see. And then, so luckily for us as hardware guys, looking at trillion parameter models is quite terrifying because we might think we have to deploy those. But there's also a strong orthogonal trend to this, which is around efficient model architectures. This is something I've worked on quite a lot in the last few years. And essentially, by designing the architecture more carefully and training the models in certain ways, essentially jumping through extra hoops, you can often achieve similar accuracy to much bigger models, but with less compute and less memory requirements. So that's kind of good news for us hardware people, I think, from the ML side. But nonetheless, in general, there's a escalating hardware demand for more memory and more, essentially, compute, more max. Given that edge device power and area budgets largely don't increase because, area budgets drive cost, power budgets drive batteries and battery life and form factor stuff. So that's not really going to change. And Moore's law doesn't really help us too much with this kind of thing anymore. So we, as architects, we really need to work at increasing energy and area efficiency on these deep learning workloads. Of course, this is kind of not news to anyone here, right? This has been ongoing, heavy area of research for the last 4 or 5 years. And I think, the good news, in my opinion, is that we're still, despite many years of research progress, I think we're still, quite early in the game of optimizing models for deep learning. We've done a lot, but I think there's plenty left to be done. And I tend to think about inference optimization across at least these 3 layers of hardware, software, machine learning. And I think the stuff we can do in all these areas, you're probably familiar with a lot of this stuff. So in terms of hardware, we can do a lot in terms of the microarchitecture of, the architecture, the microarchitecture of CPUs, GPUs, and NPUs, PU being the latest thing. And here kind of list some of those things, including emphasizing data reuse, fast convolution algorithms like Winograd, data compression. This has a big impact on memory movement cost. Often emphasize small integer data types or small FP types, and also sparse. Computation is a sort of a massive subtopic within ML hardware. The software side in the middle tends to get ignored, and ironically, it seems to be an area where we, at least at Arm Research, I think a lot of people in the industry tend to spend a lot of time solving software problems. Essentially, software is essential to allow app developers to deploy their models on hardware. And more importantly, being able to deploy them on the best hardware for that workload, so to actually get speed up, say, from an NPU or a GPU. There's also a lot that can be done there in terms of optimizing models without actually affecting their functionality or their accuracy. And then finally, on the machine learning side, there's a lot we can do there in terms of quantization, pruning, compression, and all these kinds of things, even much more researchy topics there as well. I think the reality with this stuff is there's a lot of things here that actually are kind of cross-industry challenges. A good example would be, things like int8 data types are quite well supported now, but support for things like int4 is quite patchy, and it really requires wide deployment in hardware. It requires software deployment toolchains and inference runtimes, and it requires a library of well-established model architectures that work well at those quantizations. So even something you might think is fairly easy, like quantization int4, from a research perspective, it looks quite doable, but from industry, actually, it can be a lot of challenges there. Okay, so often we want to evaluate, efficient network architectures. I spoke about this trend, and essentially, machine learning you can view as software written by software in some perspective. So it can be a flexible workload. Neural networks are somewhat malleable. We can design them to meet certain constraints. We can play with their shapes and sizes. So there's lots of scope to optimize for inference deployment, which is great for us. And we can do things like optimize the number of MACs and the model size and the activation footprint. And this has become a strong area of research in machine learning venues, and actually we've made, I think, quite impressive progress. So if you think about the standard canonical problem ImageNet, image classification, we made big progress since AlexNet. So AlexNet in 2012, 5 years later, MobileNet showed an improvement of reduction of 10x in terms of the number of MACs at the same accuracy. So that's, traditional circles, that's pretty massive improvement in terms of algorithm costs. That's 10x improvement. But then a few years later, some more recent work, that's actually been reduced by another 10x as well. So we've made strides there. The accuracy on ImageNet is almost certainly not the whole story. Deployment scenarios, there can be real challenges around generalization to out of distribution data and data shifts in general. So some of this stuff is kind of subject to further proving out in the real world, but nonetheless, it's pretty cool progress from the ML side. I think the challenge for architects and sometimes the disillusionment is when you try and run some of these optimized models on real hardware, it turns out that metrics like just looking at the number of MACs, counting the number of MACs, this often doesn't correlate well with latency on a real hardware platform, and it's hard not to sort of overstate that. Really, it's a really important point. Some things that look great on paper, such as depth-wise convolutions, are a bit of a disaster really on some hardware platforms, especially NPUs do really badly on depth-wise layers. So there's some challenges here, and let me wrap up with this slide. Essentially, the problem, as I see it, is we actually have to consider both things at the same time. We have to consider the design of the model, making it as efficient as possible, but we can't ignore the hardware, because at the end of the day, we care about the latency and energy per inference. That's nearly always what we care about, as well as the accuracy, right? So we have to evaluate both things together, and we have to design both things together. So again, I give an example of quantization where it may look good to quantize a model that use smaller data types, that's lower energy and higher throughput. But to maintain accuracy, you typically have to make the model slightly larger to accommodate that loss in capacity. So it's never clear if there's a net benefit there at ISO accuracy. We really need to consider pre-to-optimal trade-offs. So I think many people in the research community and in industry are trying to move towards sort of evaluating the network design and the model at the same time. Seems obvious, kind of tricky to do well, I think, especially given hardware availability often lags some of these ideas. It can take 18 months to 2 years to get new features into hardware that we'd like to exploit from the ML perspective. Another challenge I will mention briefly is deep learning is moving pretty quickly. I think the last 12 months, things like the popularity of transformers beyond NLP in things like vision and even audio, speech, even vision. I guess vision may one. That's quick change, and the hardware design will lag support for those things. So having flexible simulator that's simple, easy to understand, easy to hack and easy to use to evaluate models, I think is quite critical. And that's my introduction. I'm going to leave it there. Pass back to Tushar.
Great. Thanks, Paul. So let me go back and share my screen again. All right. So continuing with the introduction. So thanks, Paul, for setting up the context in terms of where we're at with DNN models and both from an application use case perspective, from a co-design perspective, and from a deployment perspective. So what I'm going to do now is kind of, do a little bit of a deeper dive and provide some relevant background on just DNNs and their computations, and a brief overview of what DNN accelerators look like before handing it off to Anand for a deeper dive into actual scale sim, right? So of course, this might be preaching to the choir, but just to set the context, deep neural networks are essentially inspired by biological neural networks, where there is this notion of neurons and synapses, and neurons are essentially the computational entities, synapses being their connections, and ultimately, like, each synapse has a weight for neuron activation. And so if you have a bunch of input activations and weights, what you're computing is a weighted sum and applying some nonlinear activation function here. So this weighted sum is, the entity that a lot of, hardware tries to accelerate, because it is a bunch of MAC operations. So within the context of deep learning, I had already mentioned at the beginning on this, this loop from model creation to training to inference. What we're going to be focusing today is on inference. And, the way inference works is, let's say you have an image, you give this to some trained neural network. It might have a bunch of convolutional layers to, let's say, extract some of the features. And then you have some additional layers at the end to summarize the features. And if you've trained your model well, it'll identify that this is actually Georgia Tech in Atlanta. So in terms of the computations in a DNN, what you see is a lot of linear algebra computation, right? So if you just think of a simple neuron that I presented in terms of its inputs and weights, what you're essentially doing is just a vector dot product, right? So the inputs are represented here by this vector, weights by this vector, and you get this nice vector. Now, if you have a bunch of neurons in a layer, and all of them with their own weights and all of them getting the same inputs, you now get into a weight matrix that you're multiplying with this input vector. So now you get to a vector matrix operation. And this is where things start becoming interesting, because you can see that data is going to get reused, right? So this same input vector is actually going to get multiplied by all of these weight vectors here. So you could reuse this input across a lot of weights. And once you have, many inputs coming in due to batches, then you also have reuse on the opposite side, right? So the same input could be reused across weights, and the same weights could be reused across inputs. So a lot of this data reuse opportunity exists inherently in the algorithm here. And at the end, what you now see is a gem operation, right? And that's one of the reasons why, gems are one of the most popular operators of computational kernels that accelerators target. Once you get to higher dimensional neural networks like CNNs, you also have this very interesting behavior where you have weight kernels that are sliding across input images. And so you actually have scenarios where filter weights are also shared across time, across the sliding window. So you get even more opportunities for reuse. Right. And so within a CNN, you would have a filter and input image. This is the dot product we were doing, and like getting in the output, you have many input channels, many filters, which generate many output channels, right? And then you could again have many input images. So what this boils down to is, each of these, you could view it and like you could kind of lower the convolution down to a gem, or you could run the convolution natively. And there's again, a lot of opportunities for reuse because of all of these loops, right? So again, I'm not going to go into a lot of detail about this. I presume many of you are familiar with this structure, but at least it sets the broad context about the computations. Okay, so you have a lot of these nice MAC operations, arranged as vector, vector, or matrix, matrix products. What are the challenges, right? And Paul alluded to this. There's millions of parameters in DNNs today. I mean, if you kind of go back to AlexNet, which had close to 4 million weights, models like Megatron have billions of parameters. And as Paul mentioned, right, we're reaching like trillion parameter transformers these days. And these lead to billions of computations, right? So at a very fundamental level, you need to be able to run all of these computations in parallel to get efficiency. The other challenge is data movement, right? So if you have these models with millions to billions of parameters, they cannot all fit on chip into your finite scratchpad memories. And as you all know, the cost of moving data becomes prohibitively more expensive as you go from on chip to off chip, and it can be close to 100 to 500x the cost to access data from DRAM compared to the cost of just performing a multiply or an add. So again, at a very fundamental level, you need to reduce energy. And so this is what has led to the rise of accelerators, right? So CPUs are kind of inefficient for the first piece, right? Even if you have a multi-core CPU, you might have 100 cores, you have billions of computations here, which is why GPUs are very popular. So GPUs have many ALUs packed together on the chip, so you get a lot of parallel compute, which is kind of why GPUs actually led to the deep learning revolution in the first case. But the big problem with GPUs is that all the communication is via memory, which is what makes them inefficient from an energy perspective. And so that's led to kind of this whole rise of this design paradigm, which is broadly called spatial, or sometimes people use the word data flow here. Like spatial accelerators essentially look like this. From a 100-foot view, you have a bunch of these processing elements that are all tightly coupled together. And the idea is, if you have billions of computations, and so the MIT idea is the Google TPU. In fact, even in some sense, the NVIDIA Tensor Core, like if you really zoom in, would look something like this, right? So you have billions of computations. Let's spread them across hundreds of ALUs, right? So that's where we want to get the parallelism benefit. And to avoid data movement, you want to reuse the data within the array via local memories and direct communication, right? So I already mentioned that there's a lot of data reuse opportunities inherently in the algorithm itself due to these, vectors and matrices. The basic idea in these accelerators is to come up with a structure where this reuse is exploited via direct forwarding or via, some of these local memory hierarchies rather than going to off-chip. So just to kind of set the stage of how all of this fits into the full system. So we are all familiar with the CPU compute model, where you have your processor and it interacts with the compiler, like which will give it a binary program, and it exposes the architecture and some of the microarchitectural knobs to this, right? And the program feeds in here. So in the DNN accelerator context, there's kind of a similar analogous behavior. So this is where your DNN accelerator comes in. It gets input activations as input, produces output activations. The problem here is your DNN model or its shape characteristics. The compiler actually often, within the compilation flow, relies heavily on these mappers, which act as optimizers to perform a bunch of loop transformations to get your code to map, or your model to map onto the accelerator. The accelerator inherently has a data flow that we'll talk about in the scale sim tutorial piece of the tutorial, and there is an implementation. And some of these details are exposed to the mapper that helps you optimize the mapping onto the accelerator, right? And so you kind of have the configuration that gets fed in for each of the layers that you're mapping here. So within this realm, one of the major challenges is that you start with your DNN model or shape. You have to map it down to your accelerator, and together this determines your energy efficiency and runtime, right? So as Paul had mentioned, just looking at the number of max in your model is not good enough, because once you actually map the model onto the accelerator, depending on the layer shape, depending on your mapping, things like utilization can vary significantly across different models or different layer types. Your bandwidth requirements can vary significantly. Some models are more compute bound versus memory bound, right? So that's kind of going to be the big focus of this tutorial, right? So we're going to focus on this box. Of course, kind of mentioning, and kind of acknowledging that you really need to get this co-design loop to work to get efficiency. But this tutorial will focus on this box, and talk about how you can model these accelerators and, understand both utilization, bandwidth requirements, and understand a lot of interesting microarchitectural, how different microarchitectural knobs are affecting performance. So this is like maybe a 10-foot view of what ScaleSim looks like. It's a simulation infrastructure that models these systolic array-based accelerators. It takes in config files, the topology file, and outputs a bunch of statistics that microarchitects can use to optimize the accelerator. So with that brief preview of ScaleSim, I'm now going to hand it off to Anand, who's actually going to do a deeper dive. So let me stop sharing